Hello.
Hi, Uncle.
Hello, Karishma. How are you?
Hello. Yeah, I'm fine.
Yeah, sorry. I have another meeting in the morning, like my time 10 to 11. That's why sometimes it
Okay, okay.
goes a bit extra. Normally,
Okay, okay.
it is, I have not missed any meeting. Like I am bit, what to say, like I am bit organized so that I know that what I have to do with all my timing. Do you get that?
Okay, Uncle. Okay.
I know the schedule and everything, but I should have said, because I was teaching the student,
Okay, okay, okay.
whole standard
Nice.
student, and at the very end there was bit of a concept I need to complete. So that took a bit of a time. Is that okay?
Okay, okay. No problem.
Okay, so last week we were getting into electric charges and then the electric
Yeah.
field around that, positive electric field and negative electric field, and we calculated the electric field strength, how to calculate that,
Yes.
and how to calculate the electric force also. And in there,
Yes.
we understood what is the permittivity, isn't it?
Yes, Uncle.
Okay. And have you, in parallel, have you linked with the gravitational field and the gravitational force? Or
Yes. Yes. Yes.
so the modeling looks like exactly similar, but only
Okay.
mass has no polarity. So there is only a
Okay.
mass. So the gravitational field will be always a positive gravitational field. There is nothing called positive or negative gravitational field. But in the case
Okay.
of our electric field, because of the nature of the charge, it can produce a positive electric field or negative electric field. That should be a good understanding. And for the same reason, in the case of the force, electric force can be attractive or repulsive. And we know when things are going to get attracted and when things are going to repel. You're okay with that?
Yes, Uncle.
Okay. So, and towards the end, we remember where we finally end last week.
Yes, Uncle. We saw a question
Ah,
on
okay.
like I don't know how to explain it. Okay, so there is one point
Uh-huh.
and the charge is acting on
Okay.
either side of it in
Okay. So like if we know the electric field strength and its direction, and when you at a point, then you bring in another charge and put it there exactly, then what will be the
yes.
force felt by that and its direction and how to calculate the magnitude? We did that, right?
Yes, yes,
Okay,
yes,
okay,
Uncle.
that's good. Okay. Okay, can you see the whiteboard?
Yes, Uncle, I can.
Okay, okay. So that is okay. So so just to extend whatever we did with the gravitational thing, because vector is a vector, right? So we are dealing with vectors. So vectors, only the name for the vector is like numbers. So once we
Okay.
know how to deal with the numbers, if like that, when we know completely about vectors, then we know how to deal with everything. So let's say I will tell you a simple case of, I have a electric field. Electric field is known here. The electric
Okay.
field value is going to be, let's say it is a 5. Let's say there is a 2i plus 3j. Okay.
Yes, Uncle.
Can you tell me, you learned this 2i plus 3j most likely in the mass. But now, as the electric field is going to be a vector quantity, I am saying at this point, there is a 2i plus 3j. What do you understand from there?
Okay, so the electric field is moving in the direction of two
No.
units in
Okay,
the.
okay, okay. Now you are saying that a vector means it has to move. Tell me why that understanding is
Oh
coming,
no,
or why that is clicking your mind. Why you are thinking that vector means it has to move.
no, it's not necessarily that it has
Yeah,
to move.
it's not about necessary. It's about
Yeah.
what quantity is that. That should tell you what I am. Like, this
Okay.
is the big mistake what we do. We actually try to impose our own comfort. Like, okay, I will do this like that, but I don't get that. That is a big mistake, right?
Yes, sir.
So our understanding has to be developed in such a way. We have to allow the quantity or what is the situation or what is happening there to tell us what is that. Take a moment
Okay.
to feel it, right?
Yes,
This is
sir.
simply a electric vector. So the electric vector, the electric field vector, it is a quantity that is there. It is not moving. Do you get that?
Yes, sir.
But if we move away from that point, its value may change. But that is a different story. Okay, so
Okay.
now
Yes.
I will try to explain what is the meaning of this electric vector. It is given in a 2i j 2i cap plus 3j, right?
Yes, sir.
So that means what? In the horizontal direction, positive horizontal direction, there is a 2 amount. Do you get that?
Yes, sir.
Okay, let's say I draw that 2 up to here to not to. Okay, let's okay, let me draw that. This is my 2i. Do you get that?
Yes, sir.
And this is going to be my 3j. Is that okay?
Yes. Yes, sir.
This is what it says. Our understanding is as somebody has already resolved that into components, that is telling us both of them are acting there. Okay.
Okay.
Is that okay? It could
Yes,
be
sir.
the strength is different. On the horizontal direction, it is, I mean, of course, the electric field vector, finally, it is going to be a units of farad per meter. Is that okay?
Yes, sir.
So this is a farad per meter. No. Sorry. Why I was thinking is a volt per meter. Is that okay?
Okay. Yes. Yes.
Okay. Volt per meter is a volt per meter. Extremely sorry. Farad per meter is for epsilon. Okay. Epsilon unit is
Oh, okay.
farad per meter. Okay. This is the farad per meter. Farad per meter. Is that okay?
Yes, sir.
Okay. So the unit is V over M. The unit is always for the magnitude part. Do you get that? Because
Yes, sir.
direction is something like is just only a direction. Okay. So somebody is saying, okay, I feel some pain. Then let's say we are trying to talk with a doctor. Then the doctor may ask where you feel the pain. Then we say, I have a pain in my head. Do you get that? Let's say,
Yeah.
then we say headache. So then the doctor may say, how much you feel about it? Like you have a severe pain, or that is the magnitude.
Yeah. Yes. Yes, sir.
So the pain strength, the quantity of the pain will be in terms of how much and the headache and the direction where that is happening is only a direction. Do you get that?
Yes, sir.
So the direction cannot, so the direction itself, it needs a unit, but the magnitude part is our volt per meter in this case. Do you get that?
Yes, sir.
So what is actually happening? So really the 3j and 2i is our convenient or somebody has given it like that, but complete the polygon. Do you see what I'm saying?
Yes, sir.
Okay, so this is our other vector, the parallel one to the I, and this is the parallel one to the. So actually the E vector is in this, it is not moving. Careful with that. Do you get that?
Yes, sir.
It is saying something like there is a, in this direction, there is a, the arrow mark is in this direction. Do you get that? I put a arrow mark in this direction. Yeah. So now I will immediately think about, let's say the E vector is actually going to be 2i plus 3j. Try to get it into 2 and 3 is going to be 4 plus 9, 13, right? Root 13.
Yeah.
Root 13 with an, it is a e power. There are a lot of ways to write it. I write it, okay, first I write it as an angle theta. Is that okay?
Yeah.
Angle theta, where theta is going to be tan inverse of our 3/2. Is that okay?
Okay, yes.
So this is one possibility. And also we can write that as a root 13 e power I theta is also fine. Do you get that?
Yes, sir.
So this is a pure our Cartesian form. Cartesian form. And this is our polar form.
Okay.
polar form. In the polar form, this is more better, which is the Euler form.
Okay.
Is that okay? No problem with this, right?
Yes, sir. No problem.
All we are saying that this root 13 is the amount of electric field, and it is in that direction. That's it.
Okay.
You get that? So the direction
Yes,
is
sir.
given by that whatever the tan inverse of 3/2. So it is not moving. It is actually telling that I am a value of root 13 at that point, but my direction is in that direction. Do you get that?
Yes, sir.
So there is one more way to write this also. Find the unit vector. So the E vector, unit vector is going to be our full E vector over the
It's mag.
magnitude. Okay, magnitude
Yes.
part we just calculated. So this is going to be 1 over root 13 of 2i plus 3j. Is that okay?
Yes, sir.
So this is another way to write it also. So the E vector can be written as whatever the magnitude part in terms of its own volt per meter unit multiplied by. So this is what I'm saying. So this will have its own volt per meter.
Okay.
And multiplied with a directional quantity is only our E at. It's a unit vector along that direction. It's just a unit. That itself is a unit.
Yes.
Do you get that? This is
Yes,
the
sir.
direction unit. Direction units. Do you get that?
Yes, sir.
So the directional units is the one we call that as the unit vector. That is why it is a unit vector. On its own, it doesn't have any extra unit. It is a direction unit. Do you get that?
Okay. Yes, sir.
Makes sense for you. This could be for anything. It could be for your moving displacement vector or direction, or it could be anything. Do you get that?
Yes, sir.
Okay, I say I have some pain in the head. So the head is the direction alone. Until we add that magnitude quantity, okay, on my head, I have something, or I have a pain, or I put a rubber band. That is the action. You do get that? The quantity
Okay.
of the action may be in that direction. Makes sense for you?
Okay. Yes, sir.
Okay. So be careful with that. Don't immediately go and attach the movement or something like that. Electric field
Okay.
is saying I am there with this much amount and my direction is that. Okay. Is it not simply like, let's say there is a charge here. Tell me what kind of charge would have produced this electric field? Positive or negative?
Positive.
Because the arrow mark is going away
Yeah.
from that point.
Yes.
Do you get that?
Yes. Yes, sir.
Okay, so I put it as, so this has to be a Q plus. Do you get that?
Okay. Yes, sir.
Let's say I put, rather, I can change because we have been provided only with the electric field, right? It is our thought process extending it. This could be the one which could have caused this. Do you get that?
Yeah. Yes.
Now I am putting a charge here. What should be the type
Negative.
of, you see, it is coming into the center.
Yeah.
This is a Q
Yes.
minus. You see, this is
Yes.
the thing we have to develop. So if a positive charge is on the tail end, the starting point of the vector, then it has to be a positive charge that could have created this particular root 13 amount of volt per meter in that direction. Do you get that?
Okay. Yes, sir.
Okay, the electric field is varying around the charge. We are quantifying that at that point. So there could be a distance in between them. Do you get that? From the point to...
Yes, sir.
Okay, so that is what we call that as the position vector is given to us as the 2i plus 3j. But the name of the vector is called, so we are saying that this is our 0, 0 for our coordinate point.
Okay.
And
Yes, sir.
automatically this become our point. This is for our positive understanding. Do you get that? This will be our 2, 3. Do you get
Yes,
that?
sir.
This is for the positive, but for the negative charge, this is our 0, 0. Do you get that?
Yes, sir.
And automatically this is our negative, because that is why it is called a floating vector. We can use it in any way. So the electric field produced by the negative charge at that point 0, 0, this coordinate point electric field would be a -2, -3. Are you okay with it?
Yes, sir.
Makes sense for you? You are not get confused, right?
No, not consistent.
You're okay. Okay, that's the
Yes.
thing. Like so, like this, if we use all our understanding, get connected, and use that, then we won't make mistake. Also, we could do much more than what they question and ask us to do and complete. You get that? So rather than attaching with somebody questioning us and increasing our knowledge, we should be like, whenever I see a quantity, I would investigate, analyze in such a way that I have clear idea about what is that. Is that okay? Okay.
Yes, uncle.
Let's keep here. This is our let's say the Q plus has created that one. Okay, it is at a distance, some distance R, but we know at that point our E vector. Now I am going to write straight away as a root 13. Do you see? I can write straight away here. Root 13 E cap. You're okay with that?
Yes, uncle.
Obviously, as it is a positive charge, this is the arrow. So now I think you are more clear picture. Nothing is moving. A charge with a Q plus at a distance R has created that. So now bring in the whole equation for our E vector. What is that? That is nothing but 1 over 4 pi epsilon, our Q plus divided by R square, and our E vector, in the unit vector in that direction. So obviously we are saying that the magnitude part, the 1 over 4 pi epsilon Q, whatever the value, divided by R square is our root 13. Do you get that?
Yes, yes, sir.
So much is our volt per meter. So this is our magnitude of the electric field at that point. And the E vector, unit vector direction is 1 over root 13.
Yes.
Our 2I. You see, this becomes more beautiful. Do you get that?
Yeah, yes, sir.
Which a one particular vector quantity in the Cartesian form should be understood this way and exaggerated. This is a possibility, one of the possibility. Do you get that?
Yes, sir.
Okay, but it is not always like this is the, so it could be lot of scenarios. Like it need not be a one charge created that. We have considered that, okay, tail end or the head part, only one charge that is possible. But it could be, first of all, it could be combination of 2 charges or 3 charges or whatever it is, but we have been given the quantity of the electric field at that point. That should be the understanding. Is that okay?
Okay, yes, sir.
Okay. So now so careful with the vector and keep going with how to extend that. When the given problem is there, add the information very carefully one above the other to extend our visualization of the problem or the situation. Then we won't make mistake in missing out any quantity, because we need to include all of them to develop our understanding and have a clear picture about, now I am ready and prepared. Don't wait for them to question or the exam paper to question. You have to calculate everything what you could do. Do you get that?
Okay, yes, uncle.
And be prepared with, if the situation is like, okay, I know that there is probably a charge Q plus created a electric field here, which is going to be 2I vector plus 3J vector. Is that okay? J cap. Okay.
Yes, yes.
So that is the arrow mark and the line is all for our own comfort. We are doing it. It is just a measured quantity that is telling us there is a electric field at that point is 2I plus 3J. That is what all about it. Do you get that?
Yes, sir.
Okay. So now what I'm saying, let's say I'm going to bring another charge here, which is going to be our Q. Okay, I'm going to bring another charge, which is Q is going to be a 2 millicoulomb. Is that okay?
Yes, sir.
Now tell me what this charge will do. What will happen to the charge? Because that is an extra information we are adding. Do you get that?
Okay, yes, sir.
Tell me, talk.
Okay. So it's plus 2 millicoulombs. So these two will repel each other.
It is not because of the plus 2 or something like that, plus 2 or even the millicoulomb or something. when you bring in a charge at the point where you know a electric field, do you get that?
Yes, uncle.
Think about what this Q itself will have. It is a quantity 2 millicoulomb. Do you get that?
Yeah.
Two information we know about it. One is it is a positive charge. Second thing is
Yes.
is amount, magnitude is 2 millicoulomb amount. Let it be.
Yes.
But it is placed on that particular point. And
Okay.
any charge will have its own property, right?
Yes, uncle.
Apart from its value of the sign of the charge and the amount of the charge, what is the other important property any charge on its own will have? What the first charge did here? Think that there will be an electric field around it.
Okay, yes, there'll be yes. Yes.
Do you get that?
Yes, uncle. Yeah.
Okay, so that is very important here. So don't just think about it. So as we placed the second charge exactly on that point, the electric field will be infinity. Do you get that?
Okay, yes, uncle.
But it would have produced another electric field here. That will be a, let's say that is our, okay, I call that as a Q2 and this as a our Q1, for example.
Okay.
So make it like this. Is that okay?
Okay, yes.
So this would have produced a E2 vector. That would be what? We know that how to calculate that because it is a 1 over 4 pi epsilon.
Yeah.
Our
Q2.
Yeah, Q2 divided by our R square. Same
R square.
Get that?
Yeah.
And we are going to have the
same of E.
Yeah, is a positive charge. So it is going to, because this vector, the E1 is actually is being given as a modulus E vector multiplied by our E cap. Do you get that? This we already calculated. That we already know that because of this quantity, the E1 magnitude itself is going to be root 13 and our E cap is our 1 over root 13 2i plus 3j. Is that okay?
Yes, sir.
So now we are going to say that this is going to be multiplied with minus E cap. You're okay with that?
Okay, yes, sir.
That's the only thing. You see that?
Yeah.
Now
Yes.
we are using the knowledge because we know the unit vector in the direction, but exactly opposite direction. That's why the minus is more than enough to help with the unit vector thing. Okay.
Okay, yes.
Now, if you see that, you can write this as separately 1 over 4 pi epsilon 1 over R square multiplied by Q2 and minus, okay, we can put the minus in the front, for example, multiplied by E cap. Is that okay?
Okay, yes.
And here we know that this is nothing but 1 over 4 pi epsilon Q1 divided by R square is our root 13. Is that okay?
Yes.
Okay. Let's say we can rewrite this as 1 over 4 pi epsilon 1 over R square is nothing but root 13 over Q1.
Okay.
Why I am doing that? You see that is this quantity. Complete this
yes,
quantity.
Sir. Yeah.
So this will be minus root 13 Q2 over Q1 E cap. You see, beautiful.
Yes.
So as it is given as a 2 millicoulomb, we can, let's say this is going to be our, definitely it has to be a positive charge because it is along that direction. I will give you, there is two possibility. Okay, let's say I give you the value for the Q1. Then tell me what is going to be other one quantity you can immediately calculate and it will be a fixed value. Let's say the complete thing is the epsilon is going to be a vacuum, for example, because don't get confused with the epsilon about what is the role played by that, because that value we know that it is 8.87 into 10 to the power of minus 11 farad per meter, right?
Meter, yes.
Okay, let it be. That numerical value is available from our data sheet or the spec sheet or whatever it is.
Yeah.
Now, I am saying that, let's say I'm going to give you Q.
R, we can calculate R. Distance.
Fantastic. That is the thing, right? It doesn't matter
Yes.
what the Q2 brought in. As soon as we know this value, then immediately R can be calculated. If I give you
Yes.
R instead of Q1, if I give you R, you can calculate the Q1. Do you see that?
Q1 can be calculated. Yes.
Yeah, you see, that is the
Yes.
understanding. You see,
Yes.
that's the beauty. So, which one you want to go about and what value you want to choose? I give you full freedom with that.
Okay. I take it as 1 millicoulomb.
Okay, take it as an example. You want a positive 1 millicoulomb is the one
Yeah.
interested. Take it as a case 1. Okay. So, case 1, we call that as Q1 is going to be 1 millicoulomb is our starting point. Then that tells us immediately. So, this is the guy. Okay, 1 over 4 pi epsilon r square, 1 over r square is going to be root 13 over 10 power minus 3. Is that okay?
Yes, sir.
Okay, so r is going to be completely a square root of, so this is going to be reciprocal. So this is going to
10 power minus.
Yeah,
10 power minus 3.
4 pi epsilon, 4 pi
root
epsilon
13.
come to the numerator and multiplied by 10 power minus 3. The whole thing will be divided by root 13. Whole thing should be square rooted. Do you get that? Is it okay?
Yes, yes, sir.
Okay.
Uncle, won't 4 pi epsilon be?
It should
okay.
be. Yeah.
The denominator.
You are right. You are right. Getting old. 10 power minus 3 is the only numerator. Yeah, you are right. Divided by root 13 or 4 pi epsilon root 13. You get
root
that?
13.
This whole has to be square rooted. Is that okay?
Yes.
And the epsilon, if you substitute like the square root of 10 power minus 3 divided by 4 multiplied by pi multiplied by 8.87 into 10 to the power of minus 11 multiplied by root 13 will give you the
we can get the value. R, the distance.
Yeah, in terms of meters. Okay, units everything should come into picture correctly. Okay, that can be done. Let's say case 2. The case 2 is, let's say I give you R is going to be something like a, say, 5 meters, for example.
And then we can find Q1.
Very good. So the Q1 could be calculated. So this will help us. The Q1 is nothing but root 3. Yeah, root 13 multiplied by 4 pi. Okay, I will write the root 13 to the other end. So that will be, you will come with the new denominator, right? All of them.
No, but now 4 pi epsilon will come in the numerator. This Q1 should come to the numerator. Yeah,
then the 4 pi, they will come to the numerator, right?
Yes.
Okay, yeah, 4 pi epsilon r square divided by
r square divided by root.
No, that is also root 13 also multiplied, isn't it? Yeah.
No, uncle, that.
Check it. So we are saying that this can be written as Q1 over 4 pi epsilon r square equal to root 13. Is that okay?
Yes, sir.
So Q1 is actually equal to
root 13. Yes.
13 multiplied by 4 pi epsilon r square.
On r square. Yeah.
There is no square root. That I did it extra as an extra nonsense. Yeah, that is not right. So this can be calculated.
Yes.
Again, this can be numerically will be 4 times pi times 8.87 into 10 to the power of minus 11 multiplied by 5 squared.
25.
The square root of 30. So much will be our coulomb.
Yes.
It's not the millicoulomb, it's the coulomb. Do you get that? So many things we could calculate. So now if you bring in the 2 millicoulomb, it will, as I said, it will calculate for each case, we could use the Q2 also. Do you get that?
Yes, sir.
Okay, so this is the electric field created by the second charge at that point. Then what we could do in extension, we could say the Q2 will be feeling a repulsive force. So I could add that as the last point. Okay, so the
Okay.
final thing what we could calculate in this problem is there will be a force felt by Q2, right? That will be simply whatever its charge value multiplied by the electric field vector created by the first charge. Similarly, there will be a force felt by the Q1 because of the whatever the charge Q1 multiplied by the electric field vector created by the second one, which is this one.
Yes, sir.
Okay, so we could happily use the 2i plus 3j. You see how far we have extended and brought the
Yes.
scenario. So these are all the things that could be done, but the education become completely opposite. What they say, they put the two charges and they give the two charges value and the distance, and then asking straight away, okay, calculate the force felt by this charge or that charge they are asking.
Yes.
You get that? And you see beauty in the case of electric field, it is a negative direction. This negative is the negative direction of this E vector. That is the first, the negative comes because of that, because the E cap is already fixed. Do you get that?
Yes, sir.
Okay. So that is saying this is fixed unit vector because we are considering this is our 0, 0. That is why this is a positive unit vector. Do you get that?
Yes, sir.
But if you look at the E2 vector, for that this is our origin. Do you get that?
Yes, sir. Yeah.
And then this become a negative. This negative will that will be 1 over root 13 within the bracket minus 2i minus 3i. That makes sense, right? So if you put the coordinates, this will be our negative j cap direction, and this will be our negative I cap direction. So because of that, this vector, so if you close this polygon for understanding, this is our negative 3j. And this is our negative 2i. No. This, this is no need. So this is a negative 2i here. This is our, this is also j itself. We get that. Parallel vector. So this is exact quantity, but we can calculate the unit vector in this direction as this unit vector will be in the value of 1 over root 13 minus 2i. Do you get that? Minus 2.
Yes.
No, minus 3j.
Minus 3j. Yes.
Okay. Any questions?
No questions.
Okay, with that, hope you can try more problems, and if you face any difficulty, note it down. We can discuss next. Okay, I will go ahead to increase the knowledge about. So in the gravitational field, we calculated the G vector can be calculated as capital G, whatever the mass value, divided by R squared G kappa. Okay.
Yes.
So in parallel on the other side, the electric field of, so we have a mass M, that is what the starting point, mass M, and then at a distance, for example, it is a mass M, and we are interested at a distance R, what is the G vector value there? Okay. So this is our gravitational field. Is that okay?
Yes, sir.
Similarly, there is a charge Q at a distance R. It would produce a electric field at that point that could be quantified as our 1 over 4 pi epsilon, whatever the Q value, divided by R squared E cap. Is that okay? So this is the this is a permanent. This is going to be always the G unit vector direction is always towards the center of the mass. But here, the E cap is dependent on the Q positive or negative. Do you get that? If it is a positive, it will be going away. If it is negative, it will be coming in. That understanding should be there. So this is our So the Q, the charge in terms of Coulomb is our Q. I also add that is a Coulomb unit and mass is a kilogram unit. And we are calculated the electric field.
Yes,
Right.
uncle.
Electric field. Now we go to the second important quantity we can go from there is, this is all about a single charge or a single mass. Is that okay?
Yes, uncle.
Remember, this is only positive. There is nothing, but here it could be positive or negative. That property should be there. Then the second thing is, if there is a, we know all about the electric field, gravitational field and electric field, then we say that, let's say there is a G vector. You get that? We know
Yes,
what
uncle.
created and what could have, it could be a single mass or many mass, doesn't matter. But let's say there is a G vector already available at a point. Do you get that?
Yes, uncle.
Now I changed from here to, I know what is here. G, I'm looking at only the, so here also I'm looking at only at the E vector. Do you get that?
Yeah, yes.
Okay. So who cares? Let's say the situation is, I know a gravitational field at a point, or I know a electric field at a point. Then what we could do, then immediately comes into a picture. This can, okay, I'm exaggerating. Now, first of all, it is going to, when you bring in another charge, do you get that?
Yes,
Sorry,
uncle.
mass, do you get that?
Yeah.
Bringing in a mass with, don't confuse with the previous M. This is a,
Okay.
yeah, we know the G vector, we are putting in a, let's say there is a mass M there. Okay. What you can tell about that? In this
That
situation,
also experiences
yeah,
no, that is
only
not
about the, because of the gravitational field existing at that point, this
Yeah.
mass will feel a gravitational force. Do you get that?
Yes. Yes, uncle.
Gravitational force. That gravitational force is going to be a vector quantity G, F vector, which is nothing but whatever the scalar quantity M multiplied by the G vector. Is it okay? Same
Yes.
thing. If you bring in a charge, which its own quantity is a Q, okay, don't confuse with the E in the previous problem. Do you get that?
Okay, yes,
We are
uncle.
saying that there is going to be a electric force. Electric force, that is going to be a force quantity also, which will be whatever the Q value, including its sign, multiplied with the E vector itself. Do you get that?
Yes, uncle.
So now, because of the, here, it doesn't matter. So this F will always be a attractive force. Do you get that?
Okay, yeah.
Attractive force, meaning whatever the direction of the G, the force will be in the same direction. M cannot change the direction of the force compared to the gravitational field. Do you get that?
Okay, yes, uncle.
But in our electric field, there are two possibilities. This can branch out to be, it could be a same as E cap when Q is positive. Sorry,
Okay.
Q is positive, because Q is positive means we say that E sign is not changing. Do you get that? E cap sign will
Yes,
be in the same direction as the F. So what is mean? If our original electric field is a positive electric field, that means the incoming charge is also a positive. Then the original electric field is going away, right? Do you get that?
Yeah, yes,
Then the force will also be going away, like it, as if it is getting repelled by the original positive, whatever the charge that created this positive electric field. Do you understand that?
Yes, uncle.
The other case is, it will be opposite to E vector when Q is negative. So that will, what will happen? So that is the minus of the Q will say the force direction is exactly opposite to the electric field direction. Is that okay?
Okay, yes, uncle.
So let's say this positive, let's say the produced electric field is a positive electric field, bring in a negative, then the direction of the force will be exactly opposite to the electric field direction. That will be an attractive force towards the whatever is created that electric field. Do you get that?
Yes, uncle.
Understanding is okay?
Yes, uncle.
Okay. Now, do you see one important thing? Okay, let's gather this together. So the next, we are going to the next understanding. Originally, there was a mass, and then that created a gravitational field at that point. And when we bring in another one, that is going to create a force. Do you get that?
Yes, uncle.
Okay, so the force is going to be in this. There is going to be a force.
Okay, yes, uncle.
So obviously, it is an attractive force, right? There is a mass here, there is another mass here. So what has happened? Don't you think that this is actually in reality, this looks like something has already happened? Because that is attractive force means these two guys should have been already touching each other, right?
Yeah.
But it has been having a distance between them as a R. Do you see that?
Yeah. Yes, uncle.
Some work has been already done in moving away these two masses for that distance amount. Do you get that?
Yes, uncle.
Some work done already. I will give you an example. Take all the things on the surface of the earth. When the Big Bang theory, whatever the Big Bang happened, and then all the things in the universe formed, don't you think that we all came from the whole earth, and everything on the earth came from the nebula, the star sun? Do you get that?
Yeah.
When it is all making a mass and everything, don't you think that this is all getting done as a very huge mass as our earth, and the infinite gravitational field was at the center of the earth? But when this Big Bang and all these things, the formation of the earth and everything happened, all items on the surface of the earth, there was some amount of energy being used in this formation of everything to keep it on the away from the center. Do you get that?
Yes, sir.
Makes sense for you?
Yeah. Yes.
Okay, so this we say that a work is done. That means energy spent. Do you get that?
Yes, sir.
Energy involved with that. This example is the spent energy GY to separate the part, to separate the masses. Do you get that?
Yes, sir.
Separate the masses by a distance R. Do you get that? We know that
Yes,
the R quantity. The same thing here. So this is going to be a charge here, and that charge has produced an electric field here as a E vector. Then we bring in another one like a Q1, Q2, for example, that would have created. So this one will be a G1 here, and I would call that as a force felt by the M2 is actually going to be M2 G1. Is that okay to make it more calculated? Do you get that? So
yes.
Here it is going to be a E1. If this is a R distance, then the Q1 will feel a force. The force felt by the Q2 is going to be the charge value Q2 multiplied by our E1 vector.
E1, yes.
Here also same thing. Some work has been done. Probably the Q1 and the Q2, they are equal and not equal. They are opposite kind of charges. They would have been already colliding together, right?
Yes,
each other. But as they are separated by R distance, there is a work already done. Let's say both of them are like charges, like both of them are negative or positive. Then they would have repelled each other and moved away, right?
Yes.
But some work is being done to keeping it in that distance without moving anywhere. Do you get that?
Yes.
So that work done. So that is also, so this energy is called we call that as the gravitational energy, or we call that as the potential energy actually.
Okay.
Potential energy. Here we say the same work done, but this is also energy, but we call that as a electric energy.
Yes.
Okay. So energy wise, the unit is going to be a joule, but let's quantify that. How to quantify the W? The W is calculated as, because the position vector in which direction we have moved, that is actually the R vector is also involved here. Do you get that?
Yes.
Do you see what I'm saying?
Yes, uncle.
Its
Yeah.
own, because we think that M1 has created all these things and our distance in that direction, the M2 has been separated. Do you understand that?
Yes, uncle.
That is a R vector is available. So now whatever the force dot product with the R vector will be our work done. Makes sense for you? Here also there is a R vector. So the work done will be equal to whatever the electric force dot product with the R vector. Is that okay?
Yes, sir.
So if the force direction and the R vector direction both are same, because in this case is all same, right? There is no other
Yes, yeah.
but the angle between them. So as they are parallel, then we could write this as nothing but modulus. One second. Okay. Sorry. I mean, next
Yeah.
meeting is starting. They are messaging me. Sorry about that.
Okay.
Okay. Do you understand that? So we
Yes,
can
sir.
say that we need to know the magnitude of this one, magnitude of this one, and then cos theta will help us, where the theta is the angle between the F and R. You're okay with that?
Yes, sir. Yeah.
So this will also be equal to our modulus F, modulus R, and cos theta.
Cos theta.
No problem with that. Is that okay?
Yes, sir. Yes, sir.
So when they are in the same direction, in the special case, we say that, let's say the cos theta is equal to 0. That means they both are parallel to each other. Is it okay?
So it will be modulus of S.
Yeah, but
modulus
the consideration parallel means it makes sense, right? Because the force felt by the mass 2 will be towards the M1, but the R vector will be away from the M1.
Yeah.
They are the opposite direction. In this case, they are exactly the opposite direction. Do you understand that?
Yes, sir.
Because we moved against the attractive force. Okay. But so in that case, it will be a 180 degree. Does that make sense?
Yes, sir.
Okay. So that will make W is actually equal to simply modulus and R. Is that okay?
Yes, sir.
No, yeah. Pi is okay. Exactly opposite, right? Do you get that?
Yes, sir. Yes, sir.
Here also in that case, here, this is quite interesting. Do you get that? So the R vector and F vector, there are two possibilities. It could be case 1, theta could be 0 itself.
Yeah.
Or 0. Tell me the situation.
I think both R and F will be in the same direction.
Yeah, but tell me the situation when what kind of charges would have, or kind of the electric field would have done that.
Okay, so it will be
in the case of masses, it is always the F vector is going to be attractive force, right?
Yeah.
But the position vector, let's say we put the reference this as the 0, 0. That's why the R vector direction is, this is our R vector direction. Do you get that?
Okay. Yes, sir.
That is why we say that between them, there is a 180 degree opposite direction. But here we are saying, let's say take the situation, R vector, we cannot help it. R vector has to be always in this, because this is our original reference.
Yeah.
R vector is in this direction. Tell me when the F2 vector will be along the R, then only it will be 0 degree, right?
Yeah. Suppose Q1's charge is, so Q2's charge should be greater than Q1's charge.
No, it's not the greater than or less than. Don't confuse with yourself. What is the magnitude to do with that? Is the kind of, so we are saying that the force direction is this. So that means what? It doesn't matter. Whatever. Let's put the Q1, you choose a sign for the Q1. You want to choose positive. Let's say it is positive, or think about from the E1 point of view, the electric vector. Electric field, if it is positive, then already this is a arrow mark in this direction, right?
Yeah.
Then what kind of charge this Q2 should be so that the force will also be in the same direction?
a positive.
Do you see that? So
Okay.
this will be a positive. Both the electric
Okay.
field is also positive, charge is also positive. This will
Okay.
also lead to our W vector is nothing but F times R. I just
Yes,
write it directly the
Yeah.
F. But we know it's a modulus and everything.
Yeah, yes.
And the
yes.
second situation is theta could be 180 degree
Yeah.
equal to pi radian. When this is possible?
Q2 is negative.
So this is the other, okay, this is positive or even negative should work. Do you get that?
Yes.
In this case, the negative should also work. Think about it. Here we have two possibilities. It is a positive negative or negative positive
Negative
should
positive.
work. That will also W equal to FR.
FR. Yes.
It's the same amount of work done, but the kind of work done is to separate them or keeping it in that distance. Do you get that?
Okay. Yeah.
Okay. Because the separating them means they are unlike charges. So this is the case of separating.
Yes, uncle. Okay.
Separating. This is a work done to bring to that.
Them.
Yeah. Bring to the place. To that position, place. Is that okay?
Yes, uncle.
Okay. I will stop here. Any questions?
No questions.
Okay. Go through this and try to
Okay.
connect it with any problem or anything you are doing. You need to don't rush it and start everything you are doing and there is a vector involved. You are increasing your knowledge in the vector also. Do you get that?
Yeah.
We should
Yes,
not
uncle.
force ourselves. Okay, I know a vector. I fixed with my thought process and knowledge about a vector. Whatever that is, I will impose on the physics. That will be completely wrong. Do you get that?
Okay.
Because we
Yes.
need to always give full consideration to what is the physics going on, and the math should support that.
Yes, uncle.
For some reason, not only you, I know many of us are thinking that vector means it is moving. Okay. Because they put a direction, right? That means moving means there is a direction means it has to move. No, why it has to, it is just a direction, right?
Yes, uncle.
It is very normal. Think in a more practical way. So let's say, somebody is asking, okay, I want to go to where you are. You may be somewhere in the T Nagar or some area, right?
Yes, uncle.
Okay. Let's say somebody is asking, where is Nellore? What do you say? It's in the north of Chennai, right?
Yes.
That means, we could use that direction for anything, but no movement has happened. You get that? You are just taking a direction.
Okay.
Don't always force that direction has to be a movement. Do you get that?
Okay. Yes.
Okay. Okay, then we see next week. Okay.
Okay. Thank you, uncle.
Okay. Take care.
Thank you. Yeah. Bye.